Previously, we discussed working with fully associative and set associative caches, but what about appropriate cache replacement policy? So we can consider that in a direct map cache that the placement policy is predetermined but for the candidate for replacement. So there isn't necessarily a choice. But what are some appropriate considerations when considering a set associative or a fully associative cache? We'll have to keep in mind appropriate temporal locality and understanding how that affects our least recently used policy. And then we'll also need to consider what factors are going to affect the fully associative policy. So in this case, we have a two-way set associative cache. And so how many LRU bits are we going to need? For this one, we're going to need just one bit. And so we want to consider what happens on every memory access. Well, we're going to set our LRU bit to either 0 or 1, and depending on if we read from or store in cache 0 or cache 1. So this additional metadata allows for us to keep track of the LRU information that we need. And each set has one LRU bit that is going to be associated with it. So what do we need to take into consideration when working with a four-way set associative cache? So let's consider the policy that the possibilities that we would have in place. So in this case, we're going to have our four caches to denote our various states that are possible. And we can have various different configurations to represent the possibilities. We have four parallel caches that are working together, which can result in almost 24 different possibilities. So will we need a state machine for this? We'll need to use as many state machines as the number of rows in the cache, and that is going to represent a lot of hardware. And so each state machine is 4 factorial states, which is going to result in a 5-bit state register that we'll need to use to encode the 24 possible states for our ordering vector. And so what happens on a context switch? When we have our TLB, we need to flush the user portion of it. With the cache, we don't need to do anything because we're using physical addresses. But one caveat associated with this with regards to a context switch is when the OS brings in a page from this to a physical page frame, hardware will invalidate the cache locations for the previous context. So let's consider on a process context switch, what happens? Does the cache entries for the process being suspended get flushed? Do the cache and the TLB entries for the process being suspended get flushed? Do TLB entries for the process being suspended get flushed? Or none of the above? And so as we just discussed, it's going to be C, the TLB entries for the process being suspended or what get flushed in this context. So let's consider when a page is evicted from a page frame in memory, what happens? Do the cache entries for the evicted page get flushed? The cache and TLB entries for the evicted page are flushed? The TLB entries for the evicted page are flushed, or none of the above? And so in this case, it's going to be B as in we will have the cache and the TLB entries flush. And the TLB, we have to flush all of them. And then the cache will typically flush all of the cache once a page is evicted. And so let's consider the mechanisms that need to be in place in order to put our TLB and virtual memory together. We previously introduced the TLBs, and then we also had our virtual page numbers and the TLB utilized to return the physical frame numbers. And so that's done if it exists in our TLB. And so there are a few considerations that we had in mind when working with the TLB in regards to speed of access and the utilization of virtual pages. So when we incorporate caches, we need to have appropriate mechanisms in place that will allow for mapping to occur for looking up the TLB given a VPN. And so with this taken into consideration processor caches, we want to consider what are going to be some of the similarities that are associated with working with a TLB in regards to mapping to appropriately direct mapped or set associative cache structure. And so this is going to be based on how the VPN is broken up into the tag and index fields for the TLB. So we have our virtual address with the VPN and page offset. And we have our physical address with a PFN and page offset, also represented by tag, index, and block offsets. When a TLB miss occurs, we go to memory, and the same thing with the cache miss. And then we can have our page fault. And so what we need to have in place is a policy that coordinates between all of these mechanisms. And that policy is going to be a proponent that persists for hardware, as well as a proponent that governs the memory management from memory in the disk in the operating system. And so in order to provide for some improvement for what might happen with a TLB miss, we can first have the TLB try to check the cache first. That will speed up if it isn't present in the TLB. So now we're able to put the TLB and the memory hierarchies together to provide for an understanding of how they interact with one another. And so the TLB access is going to be in the critical path of the cache. And so that's going to result in an increased clock cycle time. So could we possibly remove the TLB from the cache? So let's consider we have the CPU that checks the TLB, and we have a virtual address, and we have a physical address as well. We know that the page offset is going to be the same for both the virtual address as well as the physical address. So whether or not we have a hit determines if we have to go to memory or not in either case. So what we can do is we can make the cache index the same size as the page offset. And so if the page offset are the same, then the index will also be the same. And so we can map the cache index and page offset to the same. So if the page offset is 12 bits, it's gonna be represented in both the virtual and physical addresses. And if those components are the same, then we know that the index is going to be the same for both as well. And so in this case, we can have the cache and the TLB starting in parallel with one another. And so now we can introduce a virtually indexed cache or virtually indexed physically tagged cache. And in this, we want to understand how to get the TLB out of the critical path. So the cache uses a virtual index derived from the tag from the physical address. We want to keep in mind that the virtual address limits the size of the cache. So if we have a page size of 8 kilobytes, then the cache index is going to be at most 13 bytes. What we need to do is incorporate an appropriate agreement between software and hardware. And this would allow for hardware to do the address translation, and the memory manager in software will set up the VPN to PFN mapping. And so we'll have the TLB and cache access in parallel, with our index to the cache being virtual and physical is represented from our PFN. And so by implementing this, we're able to allow for a complete cache memory cycle to be saved by allowing for it to be accessed in parallel. And so in a virtually indexed, physically tagged cache, do we have the TLB and cache are accessed in parallel, or the TLB and cache are accessed sequentially? And of course, as we just said, our virtually indexed, physically tagged cache allows us to access the TLB and cache in parallel. And so is there a limitation that's associated with this implementation? Well, essentially, the limitation is that our index is what is going to determine the size of our cache. And so there is a way for us to get around this, and this is called page coloring. And with page coloring, what we're going to do is we want to provide for the ability to utilize a bigger index and thus a larger cache. And so we can have the memory manager guarantee that more of the virtual address bits will remain unchanged during the translation process. And so this is what we call page coloring. It'll allow for the processor to have a larger virtually indexed physically tagged cache that is independent on page size. And so there's a detailed example that illustrates how to accomplish this in the book. So be sure to work through that example. Now let's consider a simple memory subsystem and how things are organized. If we can consider that we'll have a block read request to service a cache miss, how will the CPU respond and how will data transfer occur in our physical system? Well, the CPU is going to send a block address to physical memory, and then that is going to be computed internally, and successive addresses of those blocks will be retrieved. And so let's assume that we have DRAM with the access time of 70 cycles, and we have a bus cycle time of 4 cycles. So if we compute the block transfer of the time for a block size of 4 words and assume that we have all 4 words are retrieved from DRAM before the data transfers to the CPU, we'll have an access time for those 4 words of 300 nanoseconds. And this is considering that we have an address that is 32 bits and a data bus of 32 bits. Now let's consider if we have an address bus of 32 bits and a data bus that is 128 bits. This results in us having a larger main memory to work with. But assuming that the DRAM access time is 70 cycles and the bus cycle time for address or data transfer is 4 cycles, given this, we have a DRAM and bus access time per block of 78 nanoseconds. And for accessing 4 words, we'll have a time of 78 nanoseconds. So this allows for us to accomplish things faster, but the downside is that we'll have 128-bit buses. So to make use of the increased bus, we can consider another way that we can improve our design, and this can occur through what we call interleaving memory or memory interleaving. Essentially what this means is that we're going to try to improve the performance of our memory subsystem. And so essentially what we'll have is various memory banks that are utilized. And within each of the banks, we're going to provide for a specific word of the cache block. So if we had a 4-word cache block size, we would have 4 banks, and the banks would be labeled from M0 to M3. So with this structure, we'd have M0 supplies word 0, M1 supplying word 1, and etc. This enables the CPU to send the block address simultaneously across all of the banks. So this means that the banks will work in parallel, and each one is going to retrieve a word of the block and is responsible for their respective word during their DRAM array cycle. So once retrieved, the banks can then turn around and send this back to the CPU. And so this allows for parallel retrieval to cut back on time. And so an example that we can consider is, that we have a 4-way interleaved memory. We can assume DRAM access time is going to be 70 cycles and memory bus cycle time is 5 cycles. How can we compute the block transfer time for a block size of 4 words and assume all 4 words are first retrieved from the DRAM before the data transfer to the CPU? Well, the thing that you want to consider with this is that we'll start memory fetches at 0, 5, 10, and 15 nanoseconds. So bank 4 memory fetch finishes at 85 nanoseconds. And then we'll have appropriate data transfers occurring from the CPU cache at 70, 75, 80, and 85 nanoseconds. And so bank 4 will finish at 90 nanoseconds. So now we can go to our question. If we have an interleaved memory, and it's going to be useful because it increases the cache block size, reduces the cache block size, allows concurrent fetches of data blocks from memory without requiring wider buses, decreases the size of the cache index. And our answer is going to be that it allows for concurrent fetches of data blocks from memory without requiring wider buses. So an example of a 4 gigabyte memory system using a 1 gigabit DRAM chip. You want to consider that this uses 2-cycle addressing using the same 15 addressing pins. And so some relative sizes and latencies you want to keep in mind is that CPU registers are typically 8 to 32. An L1 cache is going to be 32 kilobits to 128 kilobits. L2 cache is going to be 128 kilobits to 4 megabits. And main memory is going to be typically 250 megabytes to 4 gigabytes. Virtual memory can range from 1 gigabyte to 1 terabyte. And then there are appropriate latency and clock cycle times that are associated with each one of these forms of memory. And of course, we have a high-level overview of some of our terminology that we've discussed throughout this chapter.